Yeah, so yeah, very excited to be here. So today my talk is going to be about what I think we need to get to mass adoption of crypto. And the title kind of gives it away, but there's a lot of qualifiers of what exactly this means and how exactly this can work. But I want to start at the very basics. It's like, why do we need blockchains in the first place? What are we trying to get with them? And I think there are really three reasons for blockchains to exist. And the first one is we want to have self-custody of assets. And this means if I own something, nobody should be able to take it away from me without my consent. The second reason is censorship resistance of transactions, meaning if I want to transact with somebody, nobody should be able to stop me. And the third reason is trustless enforcement of commitments, meaning that if two people agreed on some commitment, they don't need to rely on a third party or trusted third party to enforce that commitment. And I would say if something doesn't provide these properties, then I would question whether it actually needs to be a blockchain. But the question really is like, let's assume we actually get to this. Is this enough for us to get to mass adoption? And I would actually say no, this is just the baseline. This is table stakes, and we actually need to get more to get to mass adoption. And in my mind, there are three other things that are needed to get to mass adoption. First one is scalability. If we have all the properties from the previous slide, but we only do 6 transactions per second, or even 100, or even 1,000 transactions per second, this is not going to yield to mass adoption. And here I define scalability a bit more strongly. This is where a network needs to be able to execute more transactions or do more computations than a single node can do. The second one is privacy. And here what I'm thinking is that people should have the option to keep their data, keep their transaction histories private, and the privacy should not be penalized with bad UX or higher costs. And this is like another property that I think is super important. And then the last one is safety. And here I don't mean safety in a context of like, I'm using safety as an overloaded word. This is not in terms of protocol safety, but more kind of safety of or ease of building safe smart contracts and interacting with them. So there are fewer hacks, there are fewer potential ways for people to lose funds, bugs are more difficult to find and exploit and all of that stuff. And so one of the things, and one of my kind of thesis is that this mass adoption is not possible on transparent chains. And what I mean by transparent chains is a chain where, or a network where the network itself executes all the transactions and has underlying data for all the transactions. And the reason why I think this is not possible, again, going back to the kind of points I made on the previous slide, there is limited scalability both in terms of computation and state that you can do if everything is transparent. If we imagine a state of the world where there are billions of people using blockchains and each of them owns like hundreds of assets, we're talking about many dozens of terabytes for just state alone, for example. The other one is, by definition, in a transparent setting, there is no real privacy. And what this means is that everybody's transaction histories and activities are fully exposed and traceable. I would say that if we somehow get to mass adoption and still have this similar state of the world as we have today, we would actually have built a dystopia. It would be much worse than a Web 2 world in which, which we're trying to get away from because, everybody's going to be fully exposed on chain. Another thing that transparent chains are really kind of adversarial and unsafe environments where everybody's code is free to examine and like once you found the bug, it's free to exploit. I think Bybit hack is an example of that. We would want to make things much more safer where finding bugs and exploiting them becomes much more difficult and not everybody can kind of exploit your smart contracts, for example, very easily as they can right now in transparent chains. So the answer to this, in my mind, is basically move as much as possible of state and execution off-chain to the client side. And to take this down kind of like through different ways of we think about execution, for example, to start out, again, the graphics are a bit shifted, but overall, like if you have a, let's say, traditional execution environment where transactions are executed one after another, users send transactions to the network, the block producer will execute them and put them into a block. Then you have a different model where you have parallel transaction execution, where users still send transactions to the network executes those transactions, but they can do it in parallel. This is a bit more flexible, a bit more efficient because now you're not limited by a single CPU, you're limited by multiple cores, maybe even multiple machines. I think the next step in evolution in this kind of chain is to take transactions and move them execution to the user side. Or user in this case could be a wallet or it could be an application. And so the user can then execute and prove the transactions and just sends the proofs to the network and the network just verifies the proofs. And not possible for every transaction, but it is possible for vast majority of transactions. But there are two important things that we need to make this work. The first one is you cannot do this without zero knowledge, because you need to prove that you've done the execution correctly, so zero knowledge is something that is absolutely required. The second thing that you need is actually a very different approach to the state and execution models, because you can do something like that, for example, in an Ethereum model where you have an ERC20 contract, and if two people want to update the contract at the same time, obviously if they prove the transition of the contract individually, you will get state contention. So you need to think differently about how state works as well. And so overall, what we want to get, as I mentioned on the previous slide, we want to have users execute and prove most of the transactions, and the network just verifies. And then we also want to have users to store most of the state locally, and then the network just stores commitment to the state. And what we need is this, the model that we want to enable is where multiple users can update the state concurrently, and we want them to be independent actors. It's not the same, so there's a difference between this and parallel execution model where, in parallel execution you can also execute multiple transactions concurrently, but it is the same actor who is doing the execution. Here you actually want independent actors to be able to do the execution. But we also want to have shared public state, because shared public state is very useful for blockchains in many ways. And kind of to summarize this, the principle, the operating principle, I think what is important, what will allow us to get to mass adoption, is we want to keep state and execution on-chain if you have to, but you can take it off-chain when you can. And so the benefits, and there are challenges to this model as well, but let's go through benefits first. So the benefits, assuming we can get there, is you basically get kind of unbounded scalability in a way that there is no need to re-execute transactions. There is no need to, you almost get basically unlimited computational complexity, because from the network standpoint, whatever gets executed locally and proven locally doesn't really impact the network kind of resources that much. There is still some resource constraints, but kind of computation is no longer a resource constraint at all. Then you get minimized state with if most of the chain is, most of the state is stored off chain. You get privacy by default with this model, where you can have public accounts, you can have private accounts, you can have encrypted accounts as well. But the privacy is kind of built in because if you execute things off-chain, and if you prove your execution, and if you store your state off-chain as well, you kind of the network doesn't know what's happening. So you get privacy by default, and it's also the cheaper option. And I'll go into this a bit later why exactly it is a cheaper option. And then you also get much safer environment because, as an example, if you don't know exactly the state of an account, you don't know what the honeypot accounts are, what needs to be hacked, so it makes the hacker's job much more difficult to figure out what needs to be hacked and how to hack it. And even if they find the bug somewhere, exploiting that bug becomes categorically more difficult. So you actually get a much safer kind of environment to work with out of the start. There are challenges with this approach because nothing is free. One of them is state management. If you move state to the client side, you need to make sure you back up your state, because if you lose your state, you kind of get locked out of your account, right? So you need to figure out how to back up the state, how to synchronize it, if you have multiple devices, or if you have multiple parties that want to update the same state at the same time. But I think this is solvable, and it's not a difficult problem to solve. The other one is proof generation latency, right? Because if you do need to generate proofs for every transaction, you actually need to spend time on the client side to generate those proofs. And proving takes time. We've made great progress in terms of reducing that. So on a high-end laptop, you can do proofs for transactions in 1 to 2 seconds. There are ways to in a short term to address it. So you can get sub-second, for example, latencies. And in the long term, proving systems will improve, the hardware will improve, and we'll be able to do it. That would not be a problem in the long term. But currently, there are some challenges. Now I want to cover how does Miden address this. So this would be a nice architecture to have, but as I mentioned, we need to reimagine a lot of things. And so here I'm going to do a very, very quick overview of Miden architecture and how we achieve these properties. So Miden puts ZK at the center of the blockchain protocol. We think how we would build a blockchain if we think zero knowledge was the core primitive that we wanted to use. And here we follow what is called an actor model. An actor model is a well-known model in distributed and concurrent systems. And there you have these actors that are independent state machines, and they interact with each other by passing messages. And these messages can be produced and consumed asynchronously. So in Miden, the way this works is that actors are accounts, and they maintain their own state and then have their, expose the interface through which the state can be updated. And we have nodes that represent messages. And you can think of nodes as kind of carrying assets and having a spend script. And spend script defines what a node, who can consume the node. You can think of a node also like as an intent, where the spend script specifies the condition, and whoever fulfills that intent can claim the node. And so a transaction in Miden actually or transfer of assets in Miden requires two transactions. The first transaction is updating the state of account 1, creating a node, moving some funds into that node, setting the spend conditions, and then the transaction 2 would be consuming the node and moving the funds into the second account. So here we decouple the state transition of first account from a state transition of a second account. And on Miden, you have the flexibility of having accounts and nodes be on-chain or off-chain. If they're on-chain, all the data is on-chain. If they're off-chain, you only put commitments on-chain, and the actual data lives on the client side or user devices or whatever it needs to be. If it's an app, it could be a server. If it's a wallet, it could be a smartphone. And so a transaction is really just state transition of one account. You only update one account in a transaction. You can read the state of many accounts, but you only update one. But you can consume and produce many nodes in the same transaction. One question that usually comes up is how does it work with a shared state? Because if you only can update one account at a time, how does shared state work? And here we can, good example would be, let's say you have something like an AMM, where let's say account 1 and account 2 are private accounts, they live off-chain, only commitments are on-chain, but Uniswap is like a public account where we want to trade with. And so the model how this works is that account 1 and account 2 can create and prove two transactions independently. They create these nodes. The nodes could specify the conditions under which the nodes can be consumed. It could be which assets do we want to swap for, what are the slippage conditions, and so on and so forth. But then the next thing what happens is the network observes that there are nodes. The network will sequence the nodes and apply them to Uniswap account. And then the network, because of this application, the nodes 3 and nodes 4 would be generated. So we have now a different mode, like transactions 1 and 2 were generated by the users. Transaction 3 is now generated by the network. And then the nodes can be consumed separately in transaction 3 and 4 by users, again, by executing local transactions and running those computations locally. So what this gives us really is that there is, because we've decoupled state transitions for each account separately, we now can generate an independent transaction, independent proof for every transaction, and you can do it for all of them in parallel. And because of that, the way this works is that, let's say there's a lot of these independent transaction proofs, and those could be generated by on the client side, or they could be generated by the network. And then the network just rolls them up into recursively into bigger proofs, or not bigger, but more encompassing proofs. And in the end, you end up with a single proof per block. And a lot of the proofs on the lower level are basically handled by the users. Like vast majority of them would be generated by users, whether it's a wallet, whether it's a specific app. And then the network mostly just verifies these proofs. And so we get this model, very flexible model, where you have different ways to think about transactions. And it really depends on where the state and execution happens. Here you have kind of like an integrated model of being able to do all of this together on a single network. And so I'll go through this. So for example, if your state is on-chain, and you also ask the network to do execution, that's network transaction. That's something that is, what typically happens on many transparent chains today. But you can have a different model where the state is on-chain, but you do execution on the client side, and that's a local transaction, so the state has to carry the state, but the execution is done by the users of their apps. And then you can have a private transaction where both state and execution happens on the client side, and the network then doesn't even know what's happening. And you get different properties. So here, privacy, you would not get privacy with the first two models if it's a network transaction or local transaction, because the state is on-chain, and for network transactions, execution is on-chain as well. You basically get no privacy. But in a private transaction, you get privacy because the network doesn't know what's happening. On the other hand, shared state is only possible for network transactions, and you may be able to get to it with the local transaction as well. And then a private transaction is not really possible to do a shared state. But the important thing is that network costs are such that you pay the most for network transactions, and you pay the least for private transactions. And I think this actually aligns the incentive correctly, because you now are asking the network to do, like, you're paying for what you're asking the network to do. So if you don't need the network to run your computation, you don't need the network to store your state, your fees would be minimal. But if you ask the network to do work for you, then you have to pay more. And I think this is what allows you to have this integrated approach where users can choose what works for their use case. I need to be public, I can be public. I want to be private, I can be private, and I actually don't have to pay as much to the network for that. Thank you.
Yeah, and with